So, after signal length, let us see further that for the ECG waveform analysis, and first we create that motivation of that there are measures like correlation coefficient and signal length. However, they provide actually the gross picture of that situation, because there could be multiple waves which can give rise to same value of the correlation coefficient or signal length, and that actually gives that idea that if we want to get more accurate answer, we need to have better measurements and we need to have more detailed analysis of these waveforms. So, from that point of view, some steps are suggested to do that part. First thing is the detection of the ECG waves, and primarily the QRS complex, because we know that QRS complex is the one which has the most energy. So, they can be detected with much more confidence, and along with the QRS complex, using that the information by the location of the QRS complex, we can possibly get the P and the Q T wave. Now, this P and the T wave we are suggesting possibly. The reason is sometimes they become more difficult to get because of noise as well as due to different abnormalities. They may not be actually that we will not be able to find them clearly. They may get actually almost lost in that noise. Okay. So, primary thing that we should get QRS complex, and with the help of that, if possible, we would take the P and the T wave for our analysis. So, the next step is that delimitation of the wave boundaries, including the P QRS T wave. So, using the information of the location of the QRS, we try to draw the boundary where the signal energies are located. So, instead of trying to find out the period here, we are interested to get the boundary of PQRST. That means, what is the starting point of P and where the T ends. So, we are interested in that, because that is the part where that action potential of that muscle tissues they are present. So, we are looking at that, and next part is that measure the interwave intervals. Now, all kinds of the measurements we can get out of the ECG signal: RR interval, PQ interval, QT interval, ST interval, QQ interval, PP interval. So, you can think of that all possible intervals we are measuring, and that actually gives us the idea that how these energies are placed or misplaced in the signal. Okay. So, though it will not give us the exact nature, that means the intensity of the waveform, but any elongation, any contraction of each of these components, that will be visible by these measurements. Next, we look at that the characterization of the shape of the signal. So, that next part would be that how the signal looks like. So, that part would be done, and in this way that we could actually get better measurement, that is the hope, that we get more information about the signal, more closely looking at that signal, but it is having one problem, that they are more difficult to handle. The reason is not just that you have to do the more computation, the main challenge is when we are taking more and more measurement, we need to think of the reliability of those measurements. If we fail in finding out the location of any one of them, for example, we are talking about the PQ segment. Now, if we cannot faithfully find out the location of P and Q, that measurement will be corrupted by errors, and that can actually change the whole scenario. We are taking that as a feature to describe the signal, and we expect that that will give us very useful information about the signal, but in that case if we get more noise, that can actually upset the whole strategy. That is why we should keep in mind that more the measurements, it becomes more to handle. Okay? So, that is the meaning of that actually wording. So, now let us look at one such scheme proposed by Cox in 1972. They have given a very simple scheme, but quite effective. What they have suggested, the duration of the width of QRS complex should be the first feature. Now, let us look at the picture again, so that it becomes clear to us that here is our P wave followed by the QRS complex and then T. So, this is P, Q, R, S and T, and the width of it, QRS complex, we can take that this is the width starting from Q to S. So, that gives us the width of the signal, that is the first actually point. Next, we look at the height. Height means when we are talking about the height, that we have the lowest point is Q and highest point is R. So, this is the height of the wave H. Okay. So, this is the height of the wave, and then we can look at that more thing, we would look at something called offset. So, let us look at the picture to get what is offset, that we have isoelectric or isopotential line is here, okay, and the midpoint of H, the midpoint of H is somewhere here. So, that the difference of that midpoint of H and the baseline, these two actually is taken as the offset. Okay. So, these are the three important the point that is taken. Let us look at the definition, that the positive or negative vertical distance from the midpoint of the baseline to the center of QRS complex. Okay. The baseline is defined as the straight line connecting the temporal boundaries of the QRS complex, and the center is defined as the midpoint between the highest and the lowest boundary in amplitude of QRS complex. So, with that we get three important actually measurements to describe the QRS complex. The first is width, next is height, two together gives that how much energy is concentrated in that and how quickly the changes are happening, and whether it is symmetric or not. We know it is not symmetric in most of the cases. So, how much is the asymmetry, that offset is giving a measure of that. So, next thing is the area under the QRS waveform rectified with respect to the straight line through the midpoint of the baseline. Okay. So, what it is suggesting, that if we have a QRS complex P QRS T so, if we can think of that the midpoint of the baseline, okay, that with respect to that, if we rectify this signal, that means this part should become positive. Now, this part would be also positive and this part is already positive. So, the area under this actually that plot, that is actually taken as another measure, which gives us some notion of actually the energy in the signal. So, based on this, they have designed a system named Argus, that, and they have done an extensive experiment with 50,000 bits, out of which that 85%, that is 54364 are normal bits were detected and classified properly, okay, and with 0.04 bits are missed. So, this gives us some idea that when we go for a complex plan, that how the things become difficult. The first part of it is to find out that every cycle, and the first step of it is to find out the bit, that is the R wave, and even for the normal signal 0.04% bits they are missed. However, good part of it, that those we could find that the bits properly for those cycles, all of them that we could actually properly classify. Next, we look at the PVCs, that 4010 of the PVCs, that is that out of that 78% are detected and classified properly, okay. And that why 78%, 5.3% bits are missed and 38 normal are falsely classified as PVCs. Okay. So, that means 0.1% of the bits they are actually falsely classified as PVCs. So, that means both that positive error and negative error both are present. We could get a reasonable accuracy, but it is far from ideal in this case. Okay. So, that motivated to do more research. We have just presented that what is the strategy to take care of this and how we can actually attempt to solve this kind of problem and design a system which can actually analyze the ECG signal and thereby we can separate out the different kind of different kind of signals. Okay? That we stop here this session. Thank you.